AB Calculus AB, Unit 8, Day 9, Lesson, Warm-Up. So let's go ahead and try the warm-up first. You can pause the video. These are some true-false questions like you'll have on your next test. Also a couple other questions that might be similar to test questions, just involving properties of definite integrals. So you got to back up your answer, true or false. You got to show something to convince me. Okay, so pause the video and try these problems. Okay, so this one right here, I mean, we could say, okay, this matches that. So then this is going to be A to A. And we know that A to A is going to be 0. So, I mean, this would be about the simplest justification, but I think I'd go for that if you did that. Otherwise, you could get the antiderivative, capital F, A to B, capital F, B to A. And that's going to be F of B minus F of A plus F of A minus F of B. And those are going to cancel. These are going to cancel. And you get 0 equals 0. So I'm going to go with true. It's not that hard, even if you do need to show the work. Now, can you break up what's inside an integral and just integrate the top and the bottom of a fraction separately? No. You can do addition and subtraction. You cannot do multiplication and division. So I think an effective way to show that this is false is to use a simple counterexample. Something maybe like power rule. So you could say, okay, well, if we were to integrate x cubed over x squared, that should be the same as our integral of x to the first, which should be x squared over 2 plus c. But if we did it this way, and tried to follow the rule that they're illustrated at the top here, and broke up the top and the bottom separately, and then this would be x to the fourth over 4, and this would be x cubed over 3, which would give you x to the fourth over 4 times 3 over x cubed, would give you 3x over 4 plus c, and these are not the same, so it is definitely false. Good quick counterexample. Number 3 is not true or false, but it uses properties of definite intervals. So I'm giving you this value. And so what I would do is this is true or false. This is. But you're pretty much going to do the problem as if they can give you the answer and find out what you would get. I break this up. Properties of definite intervals allow you to break this up. I can move the 2 out front. You got to integrate the 3. You can't just say plus 3. That's going to be the mistake people make. That's a bad mistake. So this is what we've been given. So we just put 10 there. And then here we could either integrate this. We could say, oh, well, the antiderivative is 3x. We're going to do 1 to 4. So it's going to be 12 minus 3 is 9. And that equals 29. So true. The other way is this is a constant function here. So if you're to graph it, it's just a horizontal line, y equals 3, right? And you integrate it from 1 to 4. So it's just going to be the area of a rectangle. And it's going to be base, the distance between the limits, times height. So it's really just going to be base times height, 3 times 3, which is 9. I'm okay with that also. There you go. Next one. Now, we can't hook these together for minus, but if it's plus, so we might say, okay, well, we could rewrite this and flip these limits, and that would give you an extra negative. Which would then give you a positive, right? Minus, minus, plus, plus. And now this matches that. Top and bottom of 1 has to match. Can't be the bottom both matching. It's got to be plus. So then we could hook these up and be c to b of f of x dx. And we get the same thing on both sides. So we're going to say true. Now, you could find the antiderivatives and do it that way, which works. I feel like it's less creative. It's less deep understanding, more surfacey. Number 5, I'm giving acceleration function. I'm giving initial value for velocity, and when you find the velocity function. So we got to work backwards because the integral of velocity, or velocity, is going to be the integral of v prime, which is going to be the integral of acceleration dt, which is going to be the integral of sine 2t dt. This is the work that you should show. That's going to give you, now we could do U-substitution here. I think we could get away with without U-substitution. You could do u equals 2t, du equals 2 dt. You don't want the 2. But I also could just say, oh, this is going to be negative cosine, but an extra 2 is going to pop out in front that I want, so I need 1/2 to counter it, right? So you do that. Otherwise, if you do this, it's going to be 1/2 sine u du. It's going to be negative 1/2 cosine u plus e, and then you're going to plug this back in for u, and you're going to get that. Anyways, if it's just an extra number, you can take care of the chain rule without going through all these steps. But now we need to use the initial condition to find the c value. And it should come out to 0. Now cosine of 0 is 1, so that actually means c equals positive 1/2. So your final answer is vt equals negative 1/2 cosine 2t plus 1/2. Okay, so now last lesson we talked about one-dimensional motion, rectilinear motion, motion on a line. And so a quick review of that. A lot of times we use s for position, but it could be x or y or even h. And velocity is the derivative of position, and it does include direction. And acceleration is the derivative of velocity, or the second derivative of position, and it also includes direction. S double prime equals v prime equals a. Speed is the absolute value of velocity. Moving to the right is going to be when velocity is positive, right? So it's a directional thing. Left, moving to the left, is going to be when velocity is negative. Speeding up is when velocity and acceleration have the same sign. So they could both be negative, they could both be positive. It's like you're being pushed in the direction that you're already going, right? If someone pushes you in the direction that you're already moving, it's going to push you forward, and slowing down is going to be when acceleration, when velocity and acceleration have opposite signs. So they're working against each other. Stopped is when velocity equals 0. Okay. And those are also, it could be instantly stopped when it changes direction. It actually has to go through velocity of 0. So a lot of times we call those turning points. Let's talk about gravity being thrown into these problems. So it's all the same ideas, but it's just kind of more of a specific type of scenario. So any object dropped near the surface of the Earth will have a constant acceleration, roughly, we assume. Vertical motion, there's no horizontal motion. We're just going to deal with up and down problems. We're not going to deal with also, things thrown at an angle till next year in Calc BC. That's when we do in two-dimensional motion. So the height, a lot of times you might think of it, if it's vertical motion, you might think of a height or a y value, for s. What we could do is we could work backwards from acceleration. So acceleration due to gravity is like a constant force. So we're going to work our way up here backwards, which we know how to do now. The force due to gravity is often denoted with a g, and in metric units, it's roughly about negative 9.8 meters per second squared. In English units, which we're going to often use because we're in England, we're in the United States, which rebelled against England. Oh, but England doesn't use English units. So maybe to rebel against England, we now do use English units. Anyways, even the English have decided they're not a great measuring system because they're all over the place. Metric is so much easier to use, and pretty much all the rest of the world uses it. Because we have a base 10 number system, so why not use a base 10 unit system? Oh, anyways. So this is on Earth, specifically near the surface of the Earth. Okay, if we were on another planet, it would be different on other planets, the gravitational pull. And the distance from the surface of a planet makes a difference, but relative to the size, the radius, the size, the volume of our planet, and the volume and size of the things we're talking about, it's negligible. So if we have acceleration and we want to find velocity, velocity is the integral of v prime, right? We've been doing this, which is the integral of acceleration, which is the integral of -9, or we could just start with g. Just put g in there. G is a number, dt. And g, put positive g, but g has a negative built into it because it pulls things down towards the surface of the Earth. Now g is just a number, so velocity is going to equal gt plus c. Now, usually the way we find the c value is we use what's called initial condition. In this case, a lot of times the initial velocity of the object when it's thrown or dropped or whatever at times 0, velocity equals v sub 0, v sub naught, v naught. So if we plug that in here, v naught equals g times 0 plus c, it means that c would equal v naught. So the equation for velocity due to gravity is going to be gt plus the initial velocity. So we're going to keep going. If you want to find position, you would integrate the derivative of position, which is the same thing as velocity, which is going to be gt plus v naught dt. And so s equals gt squared over 2 plus v naught t plus c. This is a different c. We're going to use the initial height, initial position. Right? So at time 0, generically we might call that s sub 0. And in this case, if you plug 0 in here for all the t's, you're going to get c equals f sub 0. So our position equation is going to be 1/2 gt squared plus v naught t plus s naught. Now, you might go ahead and just memorize these equations for gravity because it's going to be quicker than working back through it backwards every single time. Acceleration is constant. Usually I'd probably just memorize this. Now, for our equations, if we're using g is -32 feet per second, this is going to be always -16 t squared plus v naught t plus s naught. For g equals -32 feet per second squared. So that's probably what we're going to be using. Now, there's a bunch of different kind of scenarios. You could launch it from the ground. And so at t equals 0, the position is equal to 0. Or you could, launch it at some height above ground, and that's your initial position. If you drop it at t equals 0, then this is going to be your initial position, but your initial velocity is going to be 0 if you drop it, right? Just let go of it. Now, a lot of times we're going to want to figure out when it hits the ground, because that'll be the end of the problem, which will be an endpoint and possibly something we're interested in. How do we figure out when it hits the ground? Well, the thing that's always true is that s equals 0, the position equals 0, the height equals 0, and then we can find t from this and find the time of impact, which is going to be really helpful for a lot of questions. So that's kind of a quick rundown, throwing gravity into these. Now, problem in the last assignment, I'm going to go ahead and do it together with you guys. So if you didn't do it, that's fine. We can do it together now. And I didn't put it in the video because I knew I was going to do it as part of this lesson. So this is from page 329, number 26. In 1939, Joe Sprintz of the San Francisco Seals Baseball Club attempted to catch a ball dropped from a blimp at a height of 800 feet for the purpose of breaking a record for catching a ball dropped from the greatest height set preceding year by the members of the Cleveland Indians. So I don't know, it's some sort of like, you know, thing to try and get fans to come in, give bobbleheads. Oh, hey, this guy is going to catch the ball drop from a blimp. Like, yeah, let's go check that out. Or fireworks, anything other than just like baseball game, let's do something. Anyways, so someone else had done this before, less than 800 feet. So they're going to try and break the record. So hopefully they did their calculus ahead of time. Some good questions to ask you might be like, how long does it take the ball to drop? And that'll kind of help you time it. So we could start with that. Now, our initial velocity or initial position is 800 feet, right? Initial velocity is 0 feet per second. And acceleration is constant just due to gravity, negative 32 feet per second squared. Now, of course, in real life, there's a lot of other things that affect how fast something goes when it's dropped due to gravity. There's friction to the air, it's something called terminal velocity. When something's falling to, the drag due to air that pushes back on something that slows it down is related to the velocity squared. So the faster it goes, the bigger the force is. And at some point, the force equals the force of gravity. So the object stops accelerating. It's moving very fast. It's called terminal velocity, but it just doesn't speed up anymore after that. But we're ignoring all those things, okay? Now, so how long does it take? So our equation that we're writing up there is 1/2 gt squared plus v naught t plus s naught in general. That's the equation we derived. You might want to memorize that. Now for us, g is going to be negative 32. So we're going to usually have negative 16, which is half of negative 32. Negative because it's pulling the object down. Plus initial velocity was 0, right? So that's gone. Plus the initial position is 800. So this is our position equation for our baseball. And so we're going to set it equal to 0 to figure out how long it takes to get to ground level. So we're going to probably factor out the negative 16. And that's going to be what? 50. So then t squared equals 50. And we take the square root of both sides. Plus or minus, of course. Plus or minus, of course. And we could, so it's either, but we're going to go with the positive because we don't negative time. But plus or minus should be in your work. So it's the square root of 50, or you could take the square root of 25 out, and there's a 2 left over. On your calculator as a decimal, if you're interested, is 7.071 seconds. Might want to at least roughly estimate. Like, it's a little more than 7, maybe like 7.1, because square root of 49 is 7, and 64 would be 8. So it's pretty close to 7. I would guess 7.0, 7.1 seconds. All right, so we got that down. Next important question might be, well, what's the velocity in miles per hour after 800-foot drop? Like, how fast is this ball going? Like a pitcher, Major League Baseball nowadays, like a fastball could be in like the 100-mile-an-hour range. And, so that seems doable if it's like 100 miles an hour. It seems like they probably do that. So what we need to do is plug this time into our velocity equation. So our velocity equation, which we haven't figured out yet, is just the derivative of this. So if you just memorize the position equation due to gravity, you get velocity acceleration easy. You just take a derivative. That's a lot easier to go forwards and backwards. So that's your velocity. And then, so this was time to impact, by the way. So velocity, let's plug square root of 50 in here. So, that's the answer. We could take a 5 out and be negative 160 root 2. Decimal-wise, it's going to be negative 226.274. But this is feet per second. And we want miles per hour, which is probably a little easier to maybe kind of make sense of, because we generally think of miles per hour. So we got it. How many feet? Well, I think they gave us 88 feet per second equals 60 miles an hour. So we could multiply by 60 miles per hour over 88 feet per second to get rid of the feet per second. So that's my trick. If you're trying to multiply by a conversion factor, you always want the old units to be in the bottom here so they cancel out, and the new units to be on the top. So if you do this and you multiply it out, you get negative 154.278 miles per hour. So that's the velocity of the ball, and it's negative because it's coming downwards. It should be negative. Speed is just positive. Now, what happened? Because this is like a real life story. What happened was Joe did get his ball on the glove. Like he was looking straight up as it drops down, like trying to catch a fly ball, but it was coming in over 150 miles an hour. And a catcher catching a 100-mile-an-hour fastball is a little different. They have like this chest thing, and if it was really hard, it would just bump him in the chest. But Joe's looking up. The glove is between the ball and his face. So once the ball hit his glove, it smashed his glove into his face. I think he broke his nose or something. Had to go to the hospital. It was not good. And then I think he dropped the ball. I don't think he actually caught it. So I don't think the record was broken. So don't try that. Don't fire guns up in the air on New Year's Eve. Those bullets got to come back down sometime. And they'll be going as fast as they left the gun, which is fast. So anyways, that's it. There's a worksheet today where you get to practice some of this and also just some of the motion stuff that we've been doing. All right.